These are the Lesson 21 activities for college algebra. Each of the following polynomials are given in factored form. We want to find the general polynomial form, that is the non-factored form, by multiplying. Identify the degree, leading coefficient, leading term, constant term, and domain of the polynomial function. So I want to multiply these together. So I'm going to do the x plus 3 times the x plus 3 first by using the FOIL method or the lobster claw or the distributive property, however you want to call that. So first I get x squared, and then my outer terms I get 3x. Inner is also 3x, so I have plus 6x, and then lasts plus 9. And then distribute the negative 2, so I have negative 2x squared minus 12x minus 18. Okay, so the degree is the highest power of on x once you multiply everything together, so that's going to be a 2. That's your degree. And then the leading coefficient is the coefficient in front of the x to the highest power, so that would be negative 2. And the leading term, that would be negative 2x squared. The constant term is negative 18, and the domain is all real numbers. Part B. Again, I'm going to multiply these together, so I have negative x squared. I'm going to do the x plus 2, x minus 2 first. When I FOIL that, I get x squared minus 4. And then distribute the negative x squared, and I have negative x to the 4th plus 4x squared. So the degree is going to be my highest power of x, which is a 4. The leading coefficient is the coefficient in front of the x to the 4th, which in this case is a negative 1. There's just a negative sign there, but there's an imaginary 1 in front. The whole leading term is negative x to the 4th. The constant term is 0. There's no term without a x on it, so you just have an imaginary plus 0 for the constant term, and your domain is all real numbers. Now I want to look back and see if I can find a way that I could have identified the degree, the leading term, and the constant term without first multiplying. So the highest power of x I can get by adding up the exponents on x. So this is an x to the first, this is an x to the first. I add the 1 and the 1 and I get the 2. Here I have x squared, x to the first, x to the first. 2 plus 1 is 4. So that's how we could get the degrees. The leading term, I have to multiply the highest powers of x together. X times x squared times x, that gives me x to the 4th. And then the constant term, you have to multiply the lasts together, but also distribute. So here I would get 9 times the negative 2. Here I would get negative 4 times negative x squared, which is not a constant. So the constant one is a little bit harder. But you can imagine multiplying things together without doing all the work and get some of these answers. Number 2, fill in the table below to help you become more familiar with the language of polynomial functions. First row has been done for you. So my polynomial that I'm given is 2x cubed minus x squared minus 2x plus 4. The degree is the highest power of x, that would be my 3. The leading coefficient is the coefficient, the real number in front of the x cubed, which is 2. The leading term is the whole term with the highest power of x, 2x cubed. The constant term is the term with no x in it, which is a 4. The end behavior sketch depends entirely on the leading term. It is odd degree, which means the two arms do have opposite behavior. Positive leading coefficient, which means right arm up. And then my end behavior notation, as x goes to infinity, as I move to the right, the y values go up, so they go to infinity. And as x goes to negative infinity or the left, the y values go down to negative infinity. Okay, so the next one, f of x equals 3 halves x to the 5th plus 5 halves 5 halves x to the fourth minus 5 halves x cubed minus 5x squared. So the degree is the highest power of x, which is a 5. And the leading coefficient is the real number in front of the x to the fifth, which is 3 halves. The leading term is 3 halves x to the fifth. The constant term, there is not a term with no x on it in this example, so it would be a 0. End behavior sketch. I have odd degree, positive leading coefficient, so it's right arm up, left arm down. And we can describe this that as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x also goes to infinity. Goes to negative infinity because it falls to the left. Okay, third one, f of x equals negative x to the fourth times x plus 3 times x minus 3. So I'm going to multiply this out to help me answer the question. So I have negative x to the fourth times x squared minus 9. Distribute that negative x to the fourth, so I have negative x to the sixth plus 9x to the fourth. So my degree is the highest power of x, which is a 6. My leading coefficient is the real number in front of the x to the sixth, which is a negative 1. My leading term is negative x to the sixth. There is no constant term, it's 0. And then my end behavior, I have a negative leading coefficient, which means the right arm is down, and an even degree, which means both arms do the same thing. So it's both arms down here. So as x goes to infinity, the graph falls to the right, so it goes down to negative infinity. And as x goes to negative infinity, the graph also falls to the left, so also goes down to negative infinity. Number 3, we have one more characteristic to consider regarding the graphs of polynomial functions. Consider the graph of the polynomial function x cubed minus x squared minus 4x plus 4, graphed below for us. What is the degree? Highest power of x is 3. How many real zeros does f have? So zeros happen when the function equals 0. And that often happens at the x-intercepts. Okay. In fact, real zeros always happen at the x-intercepts. There might be imaginary zeros we can't see, but they want to know about real zeros. Those happen at x-intercepts. So we have 1, 2, 3 real zeros. They didn't ask me what they are yet. They just wanted to know how many. It's 3. And they happen at negative 2, 1, and 2. How many relative maximums and relative minimums, also known as extrema or turning points, does the graph have? So my turning points or my extrema happen here and here. That's 2 of them. So a lot of what we observe in this example is generally true, that the degree of the function is the number of zeros it has, and that there is going to be one less extrema than the degree. The degree is 3. The most extrema you could have is 1 less than that. So here's our conclusion. In general, if f is a polynomial function and it has degree n, the graph has at most n minus 1 extrema and at most n real zeros. Okay, it might have fewer of both of them, but that's the most it could have. Number 4, examine the graph of the polynomial function below. Find the zeros and state whether the multiplicity of each zero is even or odd. Okay, so let's work our way left to right. The first 0 I see is at negative 3. My first x-intercept's at negative 3. And it bounces off the x-axis, the graph does, so that means I have an even multiplicity. And then keep moving to the right. My next x-intercept, or 0, is at negative 1. And that goes straight through the x-axis, which means I have an odd multiplicity. It looks like it goes through and kind of looks like a line if I were to zoom in there. So I think that's actually multiplicity of 1, but it's hard to tell. Okay, keep working your way to the right. My next x-intercept happens at x equals 1. and it bounces off the x-axis there. The graph bounces off the x-axis, so I have even multiplicity. And then finally, I have a fourth x-intercept at x equals 3. Goes straight through the x-axis, which means I have odd multiplicity. How many turning points does the graph have? That is extrema. I have 1, 2, 3, 4, 5 turning points. 5 maxima or minima. And what is the lowest possible degree of this polynomial? It would have to be 6, okay? Because it has 5 turning points, the lowest possible degree would be 6. And that agrees with the zeros because I can only have at most 6 real zeros. And -3 has to happen at least twice because it's even multiplicity. So I have 1, 2, 3, odd. So the least it could happen is once. And then this is another 0 that has even multiplicity, so it has to happen at least twice. And then 3, odd multiplicity, so it would have to happen once, at least once. So 1, 2, 3, 4, 5, 6. So 5 turning points, 6 zeros. The lowest possible degree of this polynomial is 6. So I'm going to use this information, the zeros, the multiplicities, the possible degree, to write an equation of the lowest possible degree for this function. So for first, fill in each real zero. Second, fill in the multiplicities as exponents. Okay, so my factors are going to be x minus a 0, because when we do this in reverse, if you start in factored form and you want to find zeros, you set each factor to 0 and solve it. So what does this factor have to be so that when you set it equal to 0 and solve it, you get -3? It would have to be +3. Okay. And then what would this factor have to be so that when you set it to 0 and solve it, you get x equals -1? It would have to be x plus 1. And then x minus 1 and x minus 3 to get these two zeros. Now I'm going to put in the exponents as my multiplicities. So -3 is a 0 with even multiplicity. And if I want to have the lowest possible degree, the smallest even number is 2. And then I have odd multiplicity. The smallest odd is 1. Even again, I'm going to make that a 2 and then a 1. Make sure that your exponents add up to 6. 2, 3, 4, 5, 6. Okay, we're good. So this is our factored polynomial. Last thing I want to do is find the value of the leading coefficient a. Okay, I don't know what that a is. And I can use any other point on the graph, not one of the zeros, but any other point to find out what a is. So I have, I'm given a point 0, -3, the y-intercept. I'm going to make all my x's in this formula zeros. So this x becomes a 0, this x becomes a 0, this x becomes 0, and this x becomes 0. And then make the y -3, because this is an x coordinate, comma, a y coordinate. So I make all the x's the x coordinate, the y coordinate, and then the only unknown in here is a, and I can solve for it. So this becomes -3 equals a times 3 squared, which is 9, times 1, times -1 squared is +1, times -3. Okay, so I have -3 equals 9 times -3 is -27a. Divide both sides by -27, and I get a equals 1/9. So my final formula is going to be 1/9 times x plus 3 squared times x plus 1 times x minus 1 squared times x minus 3. Number 5, find the number of turning points, also known as extrema, the minimum degree, whether the degree is even or odd, and whether the leading coefficient is positive or negative for each of the following graphs. And then we can use that information to match each equation, 1 through 6, so I've got 6 equations up here, to a possible graph. Okay. We do not want to use technology. We just want to use the information we can glean from the graph. So this particular graph has 3 turning points. 1, 2, 3. 3 extrema or 3 turning points, which means its minimum degree would be 4, and it has to be bigger than or equal to 4. Is it an even or odd degree? It's even because both sides are doing the same behavior. Both sides are going down. Okay, and then is the leading coefficient positive or negative? It's negative because the right side's going down. So I want to find an equation that has these characteristics. So at least fourth degree, even degree, and negative leading coefficient. So that would be 8x squared minus x to the 4th, number 5. Okay, because the highest power of x in here is a 4. It's got a negative leading coefficient. So that one fits the bill. Okay, let's look at B. The number of turning points is 1, 2, which means its degree has to be at least 3 or bigger. Is it an even or odd degree? It's odd because the 2 arms do opposite behaviors, rises to the right and falls to the left. And is it a positive or negative leading coefficient? It's positive because it rises to the right. Okay, so now I'm going to look for an equation that satisfies all these things. Degree 3 or higher. It's got to have an odd degree that's 3 or higher and a positive leading coefficient. Okay, so that's degree 2, degree 4. Here's degree 3, but it has a negative leading coefficient. This is degree 4. Here's degree 3 with a positive leading coefficient, and here's degree 5 with a positive leading coefficient. Okay, it is tricky to decide which of these two is the appropriate equation for this graph. They both have an odd degree. One's degree 3, one's degree 5. And they both have an odd degree. They both have degree greater than or equal to 3. They both have a positive leading coefficient. So how do we decide? I could pick a point on the graph. Any point on the graph, maybe 1, -5. This point right here at 1, -5. That's an x comma a y. X, y. So x is 1, y is -5. If I put in 1 for x, do I get -5 for y in either of these graphs? So I have 1 cubed plus 3 times 1 squared minus 9 times 1. That is 4 minus 9, which is -5. So that one works. But for number 6, I would have 1 plus 2.44 minus 1.68 minus 4.8, which is -3.04. Okay, so that one is not -5. So it's got to be the cubic, number 3. Okay, part C, number of turning points is 2. 2 extrema here and here. Maximum degree then would be 3, and it has to have an odd degree because the 2 arms are in opposite directions, one up, one down. And the right arm is going down, which means I have a negative leading coefficient. So I want to find an equation that has degree 3 or higher, but it has to be odd, so 3 or 5 or 7. It has to have a negative leading coefficient. So that's 2nd degree, 4th degree. Here's a 3rd degree with a negative leading coefficient. And these two both have 3 and 5, which is odd degrees, but they have positive leading coefficients. So it's got to be this one, number 2. 3x minus x squared. Part D, number of turning points. Just one. Just the one extrema right here, which means my maximum degree would be 2. And is it even or odd? Well, the right arm is up. Oh, sorry, yeah, even or odd degree. Both arms are doing the same thing, which means it's an even degree. and the leading coefficient has to be positive because both arms are up. Okay, so let's look for an equation that does these things. It's got to have an even degree of at least 2 with a positive leading coefficient. So that could be 1. That's got degree 2, positive leading coefficient. It could be 4. That has degree 4 with a positive leading coefficient. Can't be 2. That's degree 3. It can't be 5 because that's got a negative leading coefficient. And these are both odd degree, so it needs to be even degree. So it's got to be 1 or 4. And to distinguish, I'm going to use a point. So maybe I'll use the point 0, 1, the y-intercept. Okay, so the point 0, 1 has to be on here. So if I make my x's 0 for number 1, if I made my x's 0, I would get 1 minus 0 plus 0, which is 1. Okay, but in here, if I make my x's 1, I get 1 minus 8, which is negative 7. So it can't be number 4. It's got to be number 1. 1 minus 2x plus x squared. Okay, part E, how many turning points? 1, 2, 3, 4, which means my degree has to be at least 5 or bigger. And is my degree even or odd? It's odd, because my two arms, the right arm and the left arm, are doing opposite behaviors. The right arm is up, which means I have a positive leading coefficient. So let's look for an equation that has these characteristics. It has to be at least degree 5. I only have 1 degree 5 polynomial in my list, and that's number 6. So that's got to be the one. X to the 5th plus 2.44 x to the 4th minus 1.68 x cubed minus 4.8 x squared. Okay, part F, I have 1, 2, 3 turning points, which means the maximum degree of n is 4. It is an even degree because both arms are doing the same thing. They're both up. Because the right arm is up, that means I have a positive leading coefficient. So I want a function that has at least degree 4, positive leading coefficient. I think that is going to be number 4, x to the 4th minus 8x squared. Number 6, the function f of x equals negative 49x cubed plus 806x squared plus 3,776x plus 2,503 models the number of AIDS cases diagnosed in the U.S. between 1983 and 2008. What is the degree of this polynomial? That's the highest power we see on x, which is a 3. What is the sign of the leading coefficient? It's a negative. Okay, it's a negative 49, which is a negative number. And then looking at the end behavior, if we have an odd degree with a negative leading coefficient, we are looking at this scenario, which means my end behavior as x goes to infinity, right, as time marches on, the y values are going to negative infinity. And this is not an appropriate model. We have model breakdown here because you can never have a negative number of things that you're counting. In this case, AIDS cases. Okay, so we have model breakdown. Because although cases are decreasing, you can't have a negative number. If you were to use a polynomial to model the population size of a growing city over time, would you use a positive or negative leading coefficient? Well, if the city's growing, you want the right arm to be going up like that, which means I want a positive leading coefficient.